Okay, so in this example, we're given a function f, kind of. We're not told what the rule is, but we are told that it corresponds to this graph that we see drawn here. Okay, we're asked some questions about it. So for starters, we're asked to, and part A is really where we're going to answer the question that I left off on the last page. How do you determine what the output values are for a function if all you have is the graph? Well, let's start with f of 2. So well, look for 2 on the x-axis, it's down here, and find the point on the curve that corresponds to that x value. So in other words, look up or down, depending on the nature of things, to figure out where you have to look for a point. In this case, you have to look up, right, because the graph goes above the point 2 on the x-axis. So this is the point that you're going to use to determine the output from the function f when you plug in 2. And the way you do that is you just look for the y-coordinate. So the y-coordinate of that point, well, just do this. Look over at the y-axis, and it lines up with the y value of 4, right? And this, if you actually were to write it as a point, it's the point 2, 4. That's another way to, probably an easier way to think about it, right? Whatever the y-coordinate of that point is, that's what the function is going to give you back when you plug in 2. So for that reason, we can say that f of 2 is equal to 4. So, and let's do another example, just in case that didn't make sense. Okay, so what about f of negative 2? So next we want to find f of negative 2, so go over to the x-axis and look for negative 2, and that puts you right here. So now look above, either look up or down for the function, and in this case it's down, right? We have to look down to find the function because the point on the curve is below the x-axis. Okay, so what are the coordinates of that point? That point is, well, x, or negative 2 is its x coordinate, and negative 4 is its y coordinate. So this is going to be the output value, the y coordinate of that point. So negative 4 is our output. So let's say f of 2 is 4, and f of negative 2 is negative 4. Okay, so that's the idea. Okay, so you could try a few more if you want, plug in a few other points and just test them, test yourself. In the next part, in part B, we're actually working backwards. We want to know, okay, let's say the output value is supposed to be 4. Let's say we want the output value to be 4. What would the input value have to be? Okay, well, to answer that, well, we've got a partial answer already, right? Because we know that f of 2 is equal to 4. So if you plug 2 into the function, you'll get 4. So x equals 2 seems like it may be the answer, but that might not be the only answer, right? And in general, you have to assume, and it even says, kind of gives it away. It says find all x such that f of x is equal to 4. But is there another x value you can plug into the function to get 4 back as an output? Well, to answer that question, really what you want to do is you want to say, are there any other points on the graph that have a y-coordinate of 4? And the answer is yes. There's another one right over here. Look, in general, if you found one, you want to look horizontally. Look immediately to the left or immediately to the right to try to find any other points, and you will find this one because this has the coordinates negative 6, 4, right? So that's your other solution. So and x is equal to negative 6. So there's two values of x that you can plug into the function and have the function give you back 4 as the output value. Okay, and now for part C, we want to find the y-intercept. So the y-intercept, I'm going to define that formally in a moment, but it's just look for where the graph touches the y-axis. Okay, so here's the y-axis. So you know right where to look. You don't have to look at any of this stuff or any of that stuff. Just look straight at the y-axis and look for where the graph touches it. If at all. It's possible that it doesn't, but if it does, then that's your y-intercept. And it looks like it hits the y-axis at the point negative 2. So let me just add an annotation. This is your y-intercept. So the y-intercept, actually let's just write y. Typically when you write a y-intercept, you'll just say it's a y value because it's a point on the y-axis. So we'll just say y is equal to negative 2. Okay, what about domains and ranges? Because that's what's next. Well, remember what the domain means. The domain of a function is the set of all permissible input values. So to look at the graph and try to guess what the domain is, you're basically asking the following question. You're saying, okay, for what draw a point and slide it back and forth along the x-axis. You're saying, for what point along the x-axis does there exist a corresponding point on the curve? Like, for example, if I chose this x value, well, then I'd have this, oh, I guess, well, that's a bad, let me come back to that one. That's a bad place to start. If I chose an x value of 1, well, then I'd go up, and here's the point on the curve, right? So 1 is in the domain of the function. If I chose -1, I'd have to go down, and here's a corresponding point on the curve. If I chose -3, well, here's the corresponding point on the curve. If I chose this, whatever this value is here, if I chose this value, well, there's a corresponding point on the curve directly below it. And now back to the example of 3. If I shoot straight up to 3, well, okay, so there's no visible point here, but let me delete that for a moment. If I zoom in, you probably already know where I'm going with this, but if I zoom in, what's the purpose of this arrow here drawn on the curve? It's to indicate that it keeps on going. So you have to imagine that it really does keep on going. It's just, what are you going to draw? An infinitely long graph? You can't, right? You have to stop it somewhere, but you use the arrow to indicate that it keeps on going. So if someone drew a graph like this, I would just take that to mean this curve continues and it goes on forever, and there's no x value that we can't plug in. So for that reason, I would say that the domain of f is equal to all real numbers. Now, it'd be different if there was a dot here. If there was a solid dot, then that would indicate that the graph stopped there, and then you maybe want to make a different conclusion about the domain. But we'll talk about how to handle those cases as we encounter them. So that's the domain. It's going to be all real numbers, or at least as far as we can tell from this graph. The range, that's a little more concrete too. Okay, that you're saying, okay, well, what are all the possible output values? So you're asking a different question now. You're saying, okay, what numbers along the y-axis have corresponding points on the curve? So say, for example, at least one corresponding point on the curve. So if I took this y value of 6, I'd say, okay, well, there's a point here and there's a point here. But as long as there's at least one, that's good enough, right? If I pick these points down here, any of these points, I'm going to get a point over here and a point over here. If I pick -4 as a y value, well, there is one point here that corresponds to that y value. So that -4 is in the range. But now you notice if I pick a point, anything below -4 on the y-axis, there's no corresponding point on the curve, right? If I stop there and I look to the right and I look to the left, I don't see any points on that curve. So there's no point on that curve that corresponds to, say, the y value -5. And it's the same for -4.5 or -4.1 or anything that's strictly lower than -4. But as soon as I hit -4, then the answer is yes, there is a corresponding point on the curve. It's right over here. So it's the points, I'm going to delete this now. It's the points that are less than -4 that aren't on the range, aren't in the range of this function f. So we'll say that the range of f is we just want the numbers greater than -4, but also equal to -4. So that's a perfect opportunity to use interval notation. So that's how you can get the range. It's the interval of points that are greater than or equal to -4. Okay, so we've already mentioned this, but let's just formally state it now. If you have a graph, the points at which that graph touches or crosses the x-axis are referred to as x-intercepts. Okay, so that's what x-intercepts are. And then the point that a graph touches the y-axis, or realistically it would probably cross the y-axis, is called the y-intercept. Okay, notice that one's not plural. X-intercepts I made plural, and the y-intercept is singular. That wasn't a mistake. Remember the vertical line test. If you have a function, it cannot touch the curve, or pardon me, there's no vertical line that's allowed to touch the graph of a function more than once. So if you had more than one y-intercept, well, the y-axis is a vertical line. So if you had more than one y-intercept, then actually that graph fails the vertical line test, and it's not actually a function. So if you assume that you're starting with a functions graph, you can only have one y-intercept. It might be that you don't have any at all, but you can't have more than one. But x-intercepts, you can actually have 2, you can have 3, you can have 4, you could have infinitely many intercepts. There's lots of functions that have many x-intercepts. So how do you find them? That's a concrete question you might ask. Let's say you have a function and you want to know what are the x-intercepts and what are the y-intercepts. Let's start with this one here. F of x, or f is defined by the rule f of x is equal to 3x minus 6. Let's start with the x-intercepts. Think about it this way. If you look at this graph, for example, this is an x-intercept and this is an x-intercept, right? Why don't we label that? Nothing's stopping us from doing that. These are the x-intercepts. What is the idea here? The idea is their y-coordinates are 0, right? That's what it means to be a point on the x-axis. It means you have a y-coordinate of 0. So how are you going to find them? Well, remember the y-coordinates of points correspond to the output values of the function. So really what you want to know is when is the output of this function equal to 0? So that just always solve the equation f of x is equal to 0. Solve that equation and that will tell you where the x-intercepts are for the function f. Okay, so we're going to have 3x minus 6 is equal to 0. So we can solve that equation, add 6 to both sides. You get 3x is equal to 6. And then if you divide both sides by 3, you're going to get x is equal to 2. And there you go. That's your x-intercept. And if you got more than one solution, you'll have more than one x-intercept. But if you only get one solution, then you know you only have one x-intercept. And for the y-intercept, well, go back to this example. Let me make this green just to be consistent. And that too. That's just me being distracted there, sorry. So what's special about this point, the y-intercept, where that graph crosses the y-axis? What's the x-coordinate of this point? Remember the x-intercepts had y-coordinates of 0? Well, the y-intercepts have x-coordinates of 0. So in this case, it's even more straightforward. Just plug 0 into the function. Right? Plug 0 into the function, and that will tell you where the graph touches the y-axis. Okay, so and if 0 is not in the domain of the function, then you can't plug it in. So then what will you do? Well, guess what? If that's the case, then there is no y-intercept. So you still have your answer in that case. So the upshot here is if you want the y-intercept, plug in 0. So we got f of 0 is going to be what? It's going to be 3 times 0 minus 6, which is going to give us 0 minus 6. So y equals negative 6. That is our y-intercept. Okay, so that's the idea. But this actually, as we'll see soon, you may already have recognized it. This is actually a function whose graph is a straight line. So that's a sufficient reason to say why it only hit each of the axis one time. If a curve, like this one, for example, might have more than one x-intercept. So what does that look like? Well, this next example is going to give us a look at that. So here we've got a function. We've got a y as it's written in such a way that y is defined as a function of x. So y is the output variable and x is the independent or input variable. So same idea though. If you want to find the x-intercepts, just look for where the output or where y is equal to 0. Okay, it's the same principle as what we did over here. It's just the only difference in the way we write it just comes from the fact that this function was written differently. This one was f of x is equal to 3x minus 6, so we solved f of x equals 0. We've got too many circles here. This one was written as y equals a function of x, so we solve for y equals 0. And what's that going to give you? Well, you're going to have x cubed minus 4x is equal to 0. This one takes a little more work to solve. This is an example of a cubic equation because we've got a power of x to the 3 appearing. But fortunately, we can solve this. Let me start that sentence over. Fortunately, we can factor out an x from both of those terms. Notice this has a factor of x, and so does the 4x. We can pull out an x there. So we're going to get x times x squared minus 4 is equal to 0. So that will help us solve this equation. So we've been in this situation before where we've got a product now. It's x multiplied by x squared minus 4. Okay, so where am I going with this? Well, you've got a product of two things on the left-hand side of the equation, and on the right-hand side of the equation, you have 0. I didn't write this down last time, but this is called the zero product property of the real number system. If you have any two numbers that multiply to 0, one of the two factors must be 0. That's the only way that can happen. So whenever you have a situation like this, this allows you to conclude that either x equals 0 or x squared minus 4 is equal to 0. One of those must be true. Okay, so well, that is going to be one of your x-intercepts. But then how do we find the solutions to this equation? Well, this is actually fits a very special form as well. This is referred to as a difference of squares. Let me remind you of a couple of things. Remember the difference of squares factoring formula? If you have two squares, two perfect squares, and they're subtracted from each other, so in general, let's say it's like a squared minus b squared, you can write this as the product of a minus b and a plus b. Okay, and you can do it in either direction. Sometimes you might have something like this and you can just expand it like this immediately. But quite often you have something like this and you want to factor it, so you can write it in this form. Okay, so that's a reminder. That's called the difference of squares special factoring formula. So why is that helpful here? Well, x squared minus 4, we have an equation over here. It helps to just kind of step off to the side and just look at the x squared minus 4 and just simplify that. Well, if I write that differently, because 4 is actually the square of 2. So this is x squared minus 2 squared, and that's why I reminded you of this. Because if this, think of this as the x squared minus 2 squared. So this would be your a, and this would be your b. The 2 would be your b. So just follow the format, and you're just going to get, it'll be x minus 2 times x plus 2. I'm just following this form exactly to factor it. Okay, so those details explain why I'm allowed to say this means I can go further here and say this is x minus 2, x plus 2 equals 0. Let me just draw an arrow. Okay, so that's for that specific line. Those are the details behind that specific step. Okay, well now again, what do we got here? We got a product, x minus 2 times x plus 2 is equal to 0. So the zero product property says that either x minus 2 has to be equal to 0 or x plus 2 has to equal to 0. And the only way those two things happen will be if either x is equal to 2 or x is equal to negative 2. So there's an x-intercept, there's an x-intercept, and there is an x-intercept. Let's summarize our answer. So x is equal to 0, 2, and negative 2. Those are your x-intercepts. Now, I didn't leave very much room for the y-intercepts, but the good news is you don't need much room for that. It's easier to find I accidentally said y-intercepts. It's singular, not plural. But the good news is it's more straightforward to find the y-intercept. Remember, you just have to plug in 0. That's what we did up here, right? We plugged in 0. Same thing here. So the notation you can use here is the value of y when x is equal to 0 is equal to what? Well, just plug in 0 here. X cubed minus 4x, except you're going to plug in 0. So you have 0 cubed minus 4 times 0. And that's going to give you, well, 0 cubed is 0. 4 times 0 is 0. So you just end up getting 0 minus 0, which is 0. So the y-intercept is just y equals 0. And you can, shame on me, I kind of really squished that. So if you ran out of room on your page, sorry, I hope you have some extra paper handy that you can finish those notes off on. But so the upshot here is you want to find the x-intercepts, just set the function equal to 0. Your solutions will give you the x-intercepts. If you want to find the y-intercept, just plug in 0. And whatever you get as an output value, that is your y-intercept.